In this video, we're going to look at a few different types of processes that can occur. In every single process, the first law of thermodynamics applies. This is a law. It is broadly applicable, and it applies in every scenario that we can imagine. So first, consider a piston. Here's a gas inside a chamber, and the piston can slide. We apply some heat from the surroundings, and that transfers Q into the system, into the gas. But I can specify things when we consider these processes. For example, I could say, let's keep a fixed pressure inside the gas. How do I keep the pressure fixed if we're adding all this heat? You have to turn that heat into work. So the gas expands, doing work against the surroundings. When you keep the pressure fixed, there is a name for this process, and we're going to look at those types of processes. Now, one of the ways we'll analyze the different types is using pressure-volume graphs. So what's the graph look like in this particular case? Well, pressure was constant while volume increased. So something like this. So in this video, we're going to look at the different types of processes like fixed pressure. We'll look at the PV graphs for those processes, but then we're also going to analyze some of these symbols. So in this particular case, we could say, delta U, what is that? Well, the general formula is 3/2 N times the change in temperature. But wait, nRT, where else does nRT show up? Oh yeah, the ideal gas law, or the equation of state for an ideal gas. So nRT, if this is changing, then PV must be changing. So we could write the formula like so. Now in the particular case we've got here, where there's constant pressure, only the volume changes. So we can apply the change to just the volume. But you could imagine a different case where we had something like this. Now, volume stays constant and pressure increases. So, in that type of a scenario, we would have to apply the delta to the pressure. And so we would have the change in internal energy is 3/2 delta P times the fixed volume. So this is what we're doing in the video. We're looking at types of processes, we're considering their PV graphs, and then we're pointing out any special equations that apply for these variables. There are only a few types of processes, and you've already learned the first. It's an isobaric process, which means the pressure is constant. The PV graph of an isobaric process is just a flat line. Now you can have isobaric expansion, so that the volume increases, and the way we get isobaric expansion is to heat the gas and add heat from the surroundings. That causes it to expand. But the other way you can make this happen is you can have isobaric compression, so that the volume, the X value, decreases. To produce isobaric compression, you have to cool the gas so that heat is extracted and the volume decreases. The relevant equation here is the change in internal energy is 3/2 P times delta V. And this is coming from the last slide. But as always, the work from this graph can be found by the area under the curve, P times the change in volume. On to our next process. Instead of keeping pressure constant, we could keep the volume constant, and that's called an isovolumetric process. These processes have a PV graph that looks like this. When we increase the pressure, we're heating the gas but keeping the piston fixed. The volume doesn't go up or down. We're not moving left or right on the volume axis. But instead of increasing the pressure, we could also decrease the pressure. To do that, we would have to extract heat, or Q, from the system. We extract heat by placing it in contact with a colder environment. The surroundings extract the heat. Okay, so some notable things. The equation for delta U, the change in internal energy, is 3/2 times the change in pressure times the volume. And this is coming again from 3/2 nRT. Instead of having nRT, we replace it with PV, and we realize the pressure is what changes, not the volume. Another notable equation. No work is being done. Why? There is no area under this graph. Another way to see why work is 0 is, well, the piston's not moving. So the gas isn't doing any work, and there's no work being done on the gas. There's no compression, there is no expansion. Okay, what's our next process? Well, we've kept pressure constant, we've kept volume constant. Now let's keep temperature constant. And that's called an isothermal process. What does the PV graph look like for isothermal processes? It looks something like this. That should remind you of an inverse curve. Here's the reason we get an inverse curve. This is the equation of state of an ideal gas. It tells us the pressure, the volume, the number of moles, and the temperature of the gas, or in other words, what state the gas is in. But wait a second. Number of moles doesn't change because there's no gas leaking in or out. And temperature is fixed, we say. So this whole right side is a constant. Dividing by V gives this, and we see that pressure is inversely proportional to volume when temperature is fixed. So that's why we get this type of an inverse curve for isothermal processes. There's a second thing we can say that's really important about isothermal processes. IB questions sometimes have you calculate P and V, multiply the values together, then you do that for a second data point, and you check and confirm that the two are equal. We can add some other isotherms, as they're called. The higher up the isotherm, the higher the temperature. The lower down the isotherm, the lower the fixed temperature. The final thing for us to learn is that in an isothermal process, the gas does not change its internal energy. Why? Because the temperature is fixed. If you don't change temperature, then you will not change the internal energy U. On to our final process. An adiabatic process is one where there is no energy transferred into or out of the gas. In other words, the Q, or heat, is zero. What's the pressure-volume graph look like for adiabatic processes? It's a steep curve. The notable equation for us, and we're not going to prove this like we have the others, but the notable equation is that pressure times volume to the 5/3 is equal to a constant. So if you take a first volume, raise it to this power, multiply by the pressure, then that's equal to any second volume on the curve, any second x value, to the 5/3, times the y value. If you're like me and you're the type of person who likes to see everything kind of summarized out, here is a summary of what we've learned. The only thing we don't see on this is the shape of the curves, the PV graphs. So what I encourage you to do is maybe copy this down or create a screenshot, print it out, and then cover up the different pieces of the table and recite them back. So quiz yourself. What's isobaric? Well, it's when pressure is constant. And then say in an isovolumetric expansion or compression, what's the formula for the change in internal energy? So go through this, and then for these ones in these two columns, explain why that's the case. Take a moment to just reiterate the reasons why these are true.